Alrighty, we are, or I am, back. I don't know why I refer to myself in the first person plural. My name is not Legion, for I am not many. I think. I am...
Already.
Whoa! Sorry. When I hear my own voice coming through the computer speakers, I'm not expecting it. It low-key freaks me out. Oh, hey there, Barthana. There's some stuff in the... I was hurriedly eating what looks like a little blob. Let's do it. Let's do it. So yeah, so I am open for questions. Any that you may have. I'm pulling up Outlook just to see if anybody emailed any in. Doesn't look like they have. So yeah, I'm open for business, open for questions. The one thing I will say is my kids have an activity on Tuesdays that I have to take them to, and so at about 5:10 to about 5:30. I'm gone. But then I come back. Oops. Back at 5:30, and because we miss a chunk of a 20-minute chunk for me to get them there, I extend office hours to 6:20. Okay. So anyways, that it's happened the past couple Tuesdays. They have this activity again today, and so that will be going down. Okay, sweet. Here we go. We've got questions piling up. Let's start breaking them down one at a time. All right. So, Carenza, let's see. How do we know if a molecule is nonpolar, polar, or polar covalent? Okay, great question, Carenza. Great question. Molecular polarity plays a significant role on exam 2. So this is the type of thing that you want to be getting at now. Also, I believe another reason why we want to get at this now is probably because I think that I think the lab report 5 is due today. I'm just checking that real quick. Well, anyways, regardless, couldn't find it. Okay, so how do you tell if a molecule is nonpolar, polar, or polar covalent? Okay, so the first thing that I want to say is so polar and polar covalent are the same thing. So that's the first thing. There's 2 categories of molecules. There are nonpolar molecules, and there are polar molecules. All right. So the question is, how do we determine between these two? And here's how you do that. So first off, the first thing to note is if a molecule If a molecule has no polar bonds, then it is nonpolar. All right, so that's the first thing to look for. If a molecule has no polar bonds, it's automatically nonpolar. So that's the first thing to look at. The second, so that's no polar bonds, nonpolar. Now, if a molecule there's only 3 scenarios really. Oops. Sorry, I meant to make this little arrow yellow. So next, if a molecule, let's see. So Lorenzo just asked, no polar bonds means that you have 0 difference in electronegativity. Nonpolar. Oops. Nonpolar bonds means the difference in electronegativity which is here. Between 2 atoms is 0.04 or less. So if the difference in electronegativity between 2 atoms is 0.4 or less, the bond is nonpolar. All right? And if you have no polar bonds, your molecule is nonpolar. If a molecule has polar bonds, but this is a big a big but. If a molecule has polar bonds, but it has the same atom at every position of its electronic geometry, then it is nonpolar. Alright, it's possible to have polar bonds and still be nonpolar, and that happens when you have the same atom at every position on your electronic geometry, because the dipoles cancel each other out. So this one kind of flows out of the first. All other molecules with polar bonds are polar. All right. So this is the slide that you need to determine whether or not a molecule is polar. Um, So, Corinne, which quiz are you talking about? Because it's either there's additional instructions in the problem, or there's an error. Lab 5. Let me take a look. Lab 5. Let's see, okay, let's see. If you look at oh yes, we'll do a bunch of examples. But okay. Totally gets everyone. First, let's see the fall lecture activities. Nope. I'm just checking out Lab Quiz 5. Ah. So, oh, okay. Okay. So with Lab Quiz 5, there are 2 questions about tetrahedral geometries. Okay. So there's a couple questions that say one question, and this is Lab Quiz 5. One question says to identify a non-polar tetrahedral. And there's another one that says to identify a polar tetrahedral molecule. And for the polar one, this one's okay. But I'm looking at it now. I didn't write this particular quiz. And there are two correct answers. Kate, this is what you were saying. There are actually two correct answers here, but the BH4 minus is marked incorrect in the quiz. But that is so this is one of the wrong answers, but that should not be because this molecule is nonpolar. All right, so that was a mistake in the writing of this exam, and so what I'm going to do is I'm just going to give everyone full credit for this one because that should not be there. All right, so Kate, thanks for bringing that to my attention. Also, Carenza, thanks for asking about that question. So scrolling back up, so how do you know if a molecule is polar or nonpolar? Excuse me, it all dials back to looking at the difference in electronegativity and whether or not you have the same number of atoms on all positions. So for example, so for these let's just determine polar versus nonpolar. Whoa. Determine polar versus nonpolar. Okay, so for example, let's do CF4. All right, CF4. So first, we look at our difference in electronegativity. Fluorine has an electronegativity of 4.0, carbon 2.5. So our difference here comes out to be 1.5. So that tells us that we have polar bonds. But because we have 1, 2, 3, 4 electron groups around our atom, and all of them are fluorine, the molecule is nonpolar. When you have the same atom at every position around your central atom, they all cancel each other out. So even though the individual bonds are polar, overall the molecule is nonpolar. When you swap, let's just put one fluorine with a hydrogen. All right. The difference in electronegativity for carbon and hydrogen, 2.5, 2.1, still comes out to be, well, this comes out to be nonpolar. But the difference in electronegativity between fluorine and carbon is still polar, right? That hasn't changed. So here the difference in electronegativity, 1.5. This is a polar bond. All right, and because here we've got 1, 2, 3 fluorines, but the fourth position isn't a fluorine, it's different, it's H. We don't have the same thing at every position, so this molecule is polar. All right. Awesome, awesome. Oh, you are totally welcome. Okay, so sorry, I'm scrolling back and forth because I'm answering like questions up near the top, but then peeps are commenting down below. All right, Parthana, you have been waiting patiently since yesterday for your question about exam 1. Let's take a look. All right, question is: Did the ionic charge question need signs, and were all the questions having the same marks? Okay. All right. Okay, so Parthana, which question? Alright, so let's see. I'm going to dig into exam 1. Here we go. Exam 1, let's see. Let's see, to the ionic charge question. I think it's probably these. So, Parthana, your question, did the ionic charge question need a sign? Yes, it totally did. Because there's a big difference between +3 and -3 from a ionic perspective. Okay, Carolyn, would you be able to help with Lab 6 data section on page 6.3, where we have to calculate the molarity? Totally. Yeah. Signs are not accepted? Really? That's so weird because I have signs entered for the answers. Let me just check something real quick. Here, hang on 1 second. Really? That's so weird because I had the negative ones entered as like, you know, -1 sign before the number. Yeah, that's the way, Jen, that's the way you're supposed to do. Let's see. Okay. Is it that? Oh, it looks like. Let's see what's going on with our stream. Oh, hang on. Hang on 1 second, I'm having a little bit of a technical difficulty with loading. Oh, there, maybe? Coming back? Hang on. Here, hang on. Sorry, the comment feed on YouTube just went dead, so I'm not sure if that's if you guys are seeing that or if it's just me. Give me 1 sec. Okay. All right, hang on. Why won't? Okay, I'm just gonna reboot this system. One sec, guys. I apologize. I've got my the computer that I stream from, which is fine, but then I have the one that I monitor from, and that one is spazzing out. So I'm rebooting that situation and then I'll be able to see your comments again, and get after them. I'm right now. I'm checking them on my phone. Yeah, totally. Okay, so it looks like I need to write myself a note because I'm reading everyone's comments. So let's see. Class 2. Where is... Okay, and then I need to... Okay. So, okay, so what I'm gonna do with the exam 1 ionic charge problem, since there seemed to be general confusion about how to enter negative answers. I'm just gonna give everybody full credit for let's see, what's this? I'm gonna give everyone full credit for those. I just made a note to myself to go back and do it. Bum, bum, bum. Okay, there we go. Okay, here's my comments feedback. Okay, everything seems to be rolling the way it should, except I got to log back into Canvas. We're back in business. Okay, so I'm going to, with the ionic charge stuff, I'm going to just credit everybody for that problem on the exam. With more explicit instructions in the future on the proper way to enter a negative number so that Canvas will recognize your answer as correct. Okay, Carolyn, slowly but surely, we're making our way through the comments feed. You have a question about the 5th exam, no, the 6th lab. All right, so let's take a look. Okay, so you have a question about Lab 6 data section on page 6.3. Okay. All right, let's see. Section. Oh, okay. So, Carolyn. So this is lab 6, page 6.3. This is so your question is about under the data number 5 where it says 0.1 molar silver nitrate in supernatant observation. Okay. So here for this part, there is, Carolyn, no actual calculation. This is just so just a little bit of vocabulary to make sure we're all on the same page. So we have our solution, right? We have our, this right here is our precipitate. And the liquid floating above the precipitate, this is called the supernatant. And in this part, you don't have to do a calculation. They just want you to write. They just want you to write any observations when that solution of silver nitrate is added to the supernatant. So there's nothing for you to actually calculate. They just want you to write down the observations of what you see when they add more silver nitrate to the supernatant. So hopefully that makes sense, Carolyn. Let me know if it doesn't. Awesome. Okay, good. All right, and then actually, oops. I know this is a little out of order, but I just saw it and it's quick. Let's see, for number 6, Carenza, yes, absolutely. Okay, so scrolling back up, trying to answer these as much in order as possible. Brianna, you asked a question about homework. What was that? Homework 4, question 5. Let's take a look. Homework 4, question 5. Let's load our assignments. Let's take a look. Homework 4, question 5. Okay. Oh, okay, cool. Let's take a look at this. Interesting. Okay. Yeah, checks out. So, homework 4, question 5 asks us to determine the number of non-bonding lone pairs in the Lewis structure for NO2 with a plus charge. All right, so to do this problem, we need to draw this Lewis structure, determine how many lone pairs it has, and then we will be in business. Okay, so first we got to add up our total number of electrons, right? For NO2 with a positive 1 charge. Nitrogen has 5 valence electrons. Oxygen has 6, right? And we have 2 oxygens. And then this plus charge means that we have 1 fewer electrons than we should have, so we need to subtract 1 electron from our total count, leaving us with 16 electrons in our budget. Our central atom will be nitrogen. We have 2 oxygen atoms to attach. We have to spend 2 electrons each to make those 2 bonds, leaving us with 12. You'll notice that our first oxygen has 2 electrons. It needs 6 more for a full octet, right? So we give it lone pairs 1, 2, 3, 4, 5, and 6. So we spend 6 electrons out of the budget. We've got 6 more to go, and our other oxygen is also in need of 6 electrons. So we spend our remaining 6 to complete that second oxygen's octet. Now here's the catch. All right, here's the catch. So this nitrogen right here right now has 2 bonds. All right, so that's 4 electrons. It needs a total of 8, so it needs 4 more electrons. Well, when we're missing, we can't give it anymore because we're out of electrons in our budget. So when we're out of electrons to give, the way we complete our octets is we take a lone pair and turn it into a double bond. Right now this nitrogen has access to 2, 4, 6 electrons. We're not quite at 8 yet, so we're going to take another 2 electrons, turn that into a multiple bond. Now when you look at this nitrogen, it has 4 bonds, which means it has access to 8 electrons, so we're good. Each oxygen still has access to 8 electrons, so right now this compound has, every atom has a complete octet. We put the charge on the outside. That is the Lewis structure for NO2 with a positive charge. Now, what this problem asks is it asks us to determine the number of non-bonded lone pairs in NO2, and here we have 1, 2, 3, 4. So there are 4 non-bonding lone pairs. In this molecule. Okay. So let's see. So Brianna, that is how homework 4 goes down. Homework 4, question 5. All right. Let's see. So so now I'm at Esther. Esther, you asked, how do you name this molecule? NO2. All right. So we're going to. So this is a covalent compound. It's not an ionic compound. So we use the covalent nomenclature. So this would be nitrogen dioxide. Would be how you name NO2. Okay, Esther. I'm seeing your second question. How do you count charge clouds with brackets? Okay, let's see. Oops, hey. Okay, let's see. Jen, watching a ton of YouTube videos for guidance on Lab 5. Yeah, totally. Jen, you should totally hit up as many inputs or options, as many learning tools as you can find and that you find helpful. Totally get at them. Totally. I just saw your comment about Wayne Breslin. Totally get as many voices as you can in your life articulating chemistry to you this summer. It will help you. Yes, totally, Brianna. The drawing Lewis dot structures can definitely be time consuming. Definitely something you want to practice though, because you'll want to be proficient in that material heading into exam 2. Okay, let's see. Okay, Susan, finally to your question, which you asked a while ago. Okay, let's see. Wait, hang on, Susan, before we get to yours. Okay, give me 1 sec. All right, so, Esther, when the lab, so this is lab 5. When lab 5 says charge cloud, this is what I have been calling in lecture electron groups. They are the same thing. So when you talk about how many charge clouds are in the molecule NO3, we're talking about how many electron groups are around your central atom. Right? So we can draw out the Lewis structure for NO3, which looks like this. So this is the Lewis structure for nitrate. But remember, when we talk about electron groups, this is simply the sum of the number of atoms plus the number of lone pairs around the central atom. All right, so when we talk about the number of charge clouds or electron groups in NO3, there's a charge outside, there's a bracket, but that doesn't change what you have to do. You have to look at how many groups are around your central atom. And here, in this Lewis structure, there are 3 atoms. There are 0 lone pairs around the central atom. And so there are 3 electron groups or charge clouds. Hopefully that makes sense. Let me know if it doesn't. All right, where was your first question? Susan, okay. Wait, hang on. Holy moly, we've had a lot of comments. Okay, Susan, your first question. All right, let's take a look. There we go. How is H2S considered non-polar covalent and still be considered a polar molecule? So H2S, when we look at it, here, hang on. Cakes. Yep, yep. That is exactly correct, Susan. Okay, so Susan's question is about H2S. And if you look, oh wait, I don't need my main periodic table. I need my electronegativity table. There it is. Okay, so if you look at the electronegativity for sulfur, of course. Electronegativity for sulfur is 2.5. And the electronegativity for hydrogen is 2.1. So here the difference in electronegativity is 0.4. That means these bonds are non-polar bonds. And anytime you have only 100% nonpolar bonds, not ponds, equals a non-polar molecule. So H2S is nonpolar. So Jen, your first question, sorry, I'm scrolling all the way back up, is nonpolar covalent. It is not polar. It is not polar at all. So it is 100% nonpolar because it only has nonpolar bonds. Let's see. Yes. Okay, yes. That is totally it. So H2S, which does have the same shape as water. So if we compare this to water, we have two molecules with the exact same shape. The difference is the difference between these two, it's exactly like yes, Susan, yes. Okay, so yes, the reason why water is polar and H2S is non-polar is because the electronegativity of oxygen is 3.5, hydrogen is 2.1, so the difference, The difference here, like Brianna was saying earlier, is yeah. And Susan, that is not your fault. That is oh my gosh! I'm looking at it now, where it's like non-polar covalent, polar molecule. Yes, no, that's no. It's just wrong. Because the reason why water is polar is because we're dealing with polar bonds. Yes, totally. Okay, scrolling back up. Let's see. I feel like we're getting more questions today than the last one right before the exam. Okay. 2 to 3 questions. Oh, there we did that one already. Let's see. Scrolling on down. Exam 2. What you guys want to do? Okay, that's not for me. Okay, I'm not sure what's in. Oh, okay. Kate, with a W. So for naming, here we're dealing with, again, a covalent compound, no metals. So this would be carbon, monohydrogen, trichloride. It would be quite the name. I actually asked my wife if we could name our kid carbon monohydrogen trichloride, but she said no. Okay, lab 6, where we record the weight of silver nitrate, and are we calculating the weight? Table from that video. Let's see. You refresh my. Whoa! Okay. So Karen said, to answer your question for lab 6. For lab 6, you're going to use the data. It's not the date. Use the data from the Google Sheets spread. So this is one of those ones where you're not recording the numbers that they got themselves. In the lab video, you're using the dataset provided by the link to the Google Sheets spreadsheet. Okay, let's see. Ozone metal. Okay, Kate. Another naming question. Sorry, I'm finally just now getting into these. C2H6. All right. So the prefix for 2 is di, and the prefix for 6 is hexa. So this would be dicarbon. Hexahydride. Something to remember is carbonate is one of our polyatomic ions. Carbonate is CO3 with a -2 charge. So it's something very different. And bicarbonate is another polyatomic ion. It's HCO3, the -1 charge. Okay, let's see. All right. Oh, cool. You guys are making a group study sesh. That's awesome. Yes. Corinza, that's all the data is not shown in the video. It's in that Google sheet. Oh, Jen, you were already there to help a sister out. Okay. Charge that. Oh, okay. Kate, it seemed like I answered your question or the light went on. If it didn't, let me know and I will get into it again, approach it from a different angle so it makes better sense. Let's see. Would it still be considered no lone pairs if it were... okay, Jen, great question. You, for our purposes... So Jen, for our purposes, you'd consider a single electron the same as a lone pair. So, for example, you would consider this as one lone pair, two atoms. So together, we're dealing with three electron groups. Okay, let's see. Okay, so Peyton, I just am now seeing your question. You basically have to go through your notes and build one yourself. I don't have a comprehensive list for this class at this moment in time. This is my first time teaching Chem 305 at Folsom Lake College, and every college does a slightly different book, a slightly different set of instructions. So, so that being said, you're just gonna have to construct one on your own from your notes. Okay, let's see. What is the filtrate precipitate? Okay. So, okay. Okay. Quince, I see your question. I'm just gonna hit Esther real quick with an answer to hers because it's fast. Okay. So, Carenza, let's talk about Lab 6. All right, let me pull it up. Awesome. You are welcome. Okay, so let's take a look. So real quick, what we're doing in lab 6, we're dealing with this reaction. We've got aqueous silver nitrate, which means it's dissolved in water, plus copper 2 chloride, also aqueous. And these two are reacting to form a solid plus another aqueous ionic compound. All right, and it balances out like this. All right, now you'll notice that we're dealing with mostly aqueous compounds, but we do form one solid. All right, this is the precipitate. All right, this is often abbreviated as PPT. All right, that's the precipitate. When you form the precipitate, so you've got your solution, you've got your solid clump of business right there on the bottom. This is the precipitate, and as we mentioned earlier, the solution floating above is called the supernatant. All right, so precipitate, supernatant. Next, what you do is you filter this Whoa. Ugliest Erlenmeyer flask ever. Whoa. It's a runner-up. Alright, that's a little bit better. So you filter. You're going to take all this stuff and pour it on here. Now the solution, drips down and through, but then you've got your solid stuff built up here on top. All right, so you have your filtration is how you separate your precipitate from your supernatant, and once you've separated the two, the liquid down in here is now called a filtrate. It's called a filtrate because it passed through filter paper. Alright, so the filtrate and supernatant are the same thing. It's just the supernatant doesn't become a filtrate until you actually filter it. Right. Karenza, I'll talk about that in a minute. Where that 2H2O comes from. Okay, let's see. Okay. So this is the reaction that we're dealing with. It's silver nitrate reacting with copper 2 chloride to produce a solid silver chloride precipitate and copper 2 nitrate. The reason why you have to deal with that those 2H2Os is copper 2 chloride is a hydrate. Right, you remember we dealt with hydrates in lab 4. So outside of solution, when you weigh it out, when you have copper 2 chloride in lab, it's actually 1 copper atom, 2 chloride atoms, and then there are 2 water molecules that are stuck. To the copper 2 chloride. They're stuck to every, oops. Every copper 2 chloride molecule that isn't dissolved in water. All right, so this is for solid, but in the aqueous phase, we just write it as copper 2 chloride because in the aqueous phase, this, AQ, means dissolved in water. and everything in the aqueous phase is dissolved in water. There's water all around. So when you write a chemical reaction and you're dealing with copper 2 chloride in the aqueous phase, you don't write it as a hydrate because it's dissolved. But when it's a solid, that's when you write that dot 2H2O, because as a solid, copper 2 chloride is so hygroscopic that every one molecule of copper 2 chloride has 2 water molecules stuck to it, attached to it. So that's why we do that. Okay. So let's see here. Okay, so you've got a question on okay, so Carenza, when they say so whoops, nope. So we're still dealing with lab 6. This would be page 6.3. When they say, so there's a space where they say moles, they want you to calculate the moles of original AgNO3. Honestly, they just want you to calculate the moles of AgNO3, right? Here, in other words, they want you to calculate moles of this reactant. And you do that by taking the grams of AgNO3 and multiplying by the molecular weight. Okay. I have one more thing to say. Hopefully that's enough to get you started with the exception of when they ask you for moles of your copper 2 chloride, and they say of original copper 2 chloride, but as we've established, it's just the moles of reactant. Here, you're going to calculate this in the same way, right? You've got your grams of copper 2 chloride. To find your moles, you got to multiply this by the molecular weight. That's how you find moles. But something to be aware of. When you calculate the molecular weight, there's 1 copper, 2 chlorides, and 2 water molecules. Alright, so you've got to add all of these. And plug that in there. Whoa. Alright, so that's where the hydrate comes into play, is you have to include those 2 water molecules in your calculation of molecular mass. So hopefully that gives enough to get started. Okay. Let me know if you need kind of more explanation along those lines. I'm totally down to give it to you. But see if this is enough to get you started. I'm going to circle back around, and there's some other questions I haven't gotten to. So I'm going to circle back and get to those. Okay. Kate. Lab 5. So you have a question? Okay. So Kate, your question, where was it? Okay, right here. How do we find the number of valence electrons? All right, where are we? Here we go. Lab 5. So the way you do that is you actually have to consult the periodic table. To find the number of valence electrons, you have to take a look at the periodic table. So, for example, if we just if we calculated the number of valence electrons for NF3, all right? So the number of valence electrons, there's a quick and easy way to determine that for the main group. If we just look at the main group, the first column has 1 valence electron, the second column has 2, 3, 4, 5, 6, and 7. All right, so we have to determine the number of valence electrons in this molecule. We have to locate nitrogen. Okay, nitrogen is in column 5. So there are 5 valence electrons there. Next we do fluorine. Fluorine is in column 7. That means it'll have 7 valence electrons, but we have 3 fluorines in this molecule, so we need to multiply that 7 by 3. So 3 times 7 is 21. 21 plus 5 is 26. So nitrogen trifluoride has 26 valence electrons. And Kate, you can use the periodic table as your quick guide to determine how many valence electrons each atom has. Then you total them up. Excuse me, and that is your number of valence electrons. Okay. Oh, shoot. Okay, well, we're just going to go like this. All right, Susan. Susan, let's see. Is CO considered a polar molecule or non? Okay. So something to keep in mind as an FYI is only polar molecules have dipoles. So to say that a molecule is polar is to say that it has a dipole. All right. So now when you look at carbon monoxide, this is its structure, and oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.5. So here the electronegativity difference is 1.0. This falls squarely in the polar range. So this molecule is polar because, again, it doesn't have an oxygen on every position. There's two positions, only one oxygen. So this molecule is polar. Okay, yes, yeah, that is totally correct. Oops. Okay. All right, let's see. Okay, Susan, you have another great question with molecules like oops, hang on. There we go. C2H6 or C2H4 or even C2H2. Your question is a good one. The question is, how do we, I spelled we with two E's, it's been a long day, determine charge clouds? All right, and the answer is you can't do it for the whole molecule. You can only do it for individual atoms within the molecule. So, for example, let me make a little space here. So sorry, Photoshop was freezing just a little bit. So we've got, for C2H6, the Lewis structure looks like this. And when it comes to charge clouds, you could say, oops, that actually I'm going to move them over here. So we could say, you could say, look at this carbon that I'm boxing in yellow. This carbon has 4 atoms, 0 lone pairs, so it'll have 4 charge clouds or electron groups. And we'd have to do the same for this atom. This atom in green has 4 atoms, 0 lone pairs. So we would say it has 4 charge clouds or electron groups. All right. When you no longer have a central atom in play, as is the case with all of these molecules actually, you no longer can give a geometry to the entire molecule. You can only look at an individual atom and say this individual atom is tetrahedral because it has 4 electron groups, or this individual atom has 3 atoms attached, 0 lone pairs, so this would have 3 electron groups, or it would be trigonal planar. I'm not exactly sure what you mean. Let's see. Oh, sorry. Sorry, I just wasn't exactly sure what you were referring to. Does this make sense though? When we talk about electron groups or electron clouds, those are only really useful when there's one central atom. But for molecules like C2H6 or C2H4, there is no, it is kind of hard, yeah. There is no central atom involved, and so talking about charge clouds or electron groups becomes less useful, less meaningful because of that. Okay. All right, let's see. What does it mean? What does any of it mean? Let's see. Okay, let's see. Where are we? Okay. Net weight. Oh! Okay, hang on. Let me pull something up real quick. All right, so this is, I finally just got to Carolyn's comment about net weight. So here's so you know in the what's that thing called? The Google Sheet. It tells you the mass of the filter paper plus the precipitate, and it also gives you just the mass of the filter paper. Oh, paper. The filter paper. If you took the difference of these, if you subtracted one from the other, what you'd have left is just the mass of the precipitate, right? And this mass of precipitate right here this is called the net weight because we took the difference. Of two masses to find it. One subtracted from the other. Whoa. Alright, so that's just what they're talking about when they talk about the net weight of silver chloride precipitate. Alright, save. Question 9, lab 6. I'm not sure how to include more coefficient for chlorine. Okay, let me look. Alright, let's see. Percent of original chloride used. Okay. Lab 6. Question 9 is on page 6.4. Okay, so they want to know the percent of chloride ions used. All right? They want to know the percent of chloride ions used in this chemical reaction. Well, the percent of chloride ions used would have to be equal to, equal to chloride used divided by the total chloride ions available times 100, right? And we could use any units for these. We could use mass, we could use moles. You know what, I'm thinking let's just use moles because I actually think it'll be slightly less math. So let's set up this equation as follows: as moles of chloride used over total moles of chloride. All right, now the total moles of chloride, well, that would be the moles. We'd have to get this from our copper 2 chloride dihydrate. Right, because that is how many moles that we get total. The moles of chloride that got used in this reaction this would come from the ones that reacted, the ones that were used, would come from the amount of silver chloride precipitate that formed. All right? So you would, to get your total, moles of chloride, you take your grams CuCl2 and convert it to moles. Right, you put your molecular mass in the denominator. And 1 mole in the numerator. Oops. All right, then, so these two would cancel. But then you don't want moles of copper 2 chloride dihydrate. You want moles of just chloride, right? We want to know just the moles of Cl minus. And this ratio you get from the equation. In 1 molecule of copper 2 chloride dihydrate, in one of these molecules, there are 2 chloride ions. So that ratio there is 1 to 2. Now these two cancel. That's how you get your total. To find the amount that was used, you take your mass of your precipitate, and again, we're going to convert these to moles, so we're going to put grams of silver chloride in the denominator, 1 mole in the numerator. Then, this is all well and good, right? Silver chloride cancels. We need to do one more conversion because we don't want to know the moles of silver chloride formed. We just want the moles of chloride ion. And here, there is, in 1 molecule of silver chloride, there is 1 chloride ion, so that is a 1-to-1 mole ratio. So this is the calculation that you follow to find your denominator, the total. This is the calculation you follow to find your numerator, the used, and then you just plug one to the other. And that is how you set this calculation up. And then say, where it says, you said you're not sure how to use the molar coefficient. That part with, they mentioned be careful of the molar coefficients. That is this part. and this part. So they're just saying be careful there. Because with silver chloride, it's a 1-to-1 ratio, moles of silver chloride to moles of chloride. For copper 2 chloride dihydrate, it is a 1-to-2 molar ratio. So that is all they're talking about there. And hopefully that puts you on the path. Yes, exactly. Exactly right. Of course. Okay, Jen, let's see. Lab 6, question 2. Multiplying the masses. Okay, so quick. Awesome. Glad to hear it. You are welcome, Carenza. You are absolutely welcome. Jen, quick clarification. Is it question 2 of the data analysis? Okay, good. Because I was like scrolling through and there were like 3 different question 2s. I wanted to make sure I was had my eye in on the correct one. Okay. So here they want you to calculate the okay, so let me repeat your question. Okay. Jen, great question. So here in hydrate nomenclature, this dot means stuck to. It does not mean multiply. So it's literally copper plus 2 chlorines plus 2 times 2 hydrogens plus oxygen, where you're punching in the AMU for all of these dudes. But it's literally copper plus chloride plus hydrogen so it's not multiplied together. That dot doesn't mean multiply. It just means add the mass of 2 water molecules onto the mass of your copper chloride. So another way to look at it is add the mass of 2 waters Awesome. Okay, good. Okay, let's see here. A couple things. Question 8. We use the answers for 1 and 3, right? Yep. At Carenza. Totally. 1 and 3 are set up for 8. Okay, Esther, let's see. I've noticed that some of the compounds on lap 5 so are called ethane. Okay, Esther, great observation. You are welcome, Carenza. Okay, Susan, homework 4, number 2. Let me pull that up. Okay, Susan, ask us to find a molecule that only has single bonds. Okay, well, so let's give it a look. Which molecule only has single bonds? And then they give us NBr3, CS2, CS, CO, O2. Quick reminder. A single would be like this, or here. Let me go even simpler. It's a single. A double would be like O2. And a triple would be like N2. All right, so the only way to solve this is to draw the Lewis structures. For each until you find one with only single bonds. Carenza, great question. All right, just a quick FYI. I have to step out for a little bit. Gonna drop my kids at their activity. I will be back in about 20 minutes. It's really close to our house. So I'll be back at 5:30. And you won't be losing any time. I'll stay 20 minutes over. Yeah. So here's what you do. Alrighty, I will be back as quickly as I can. I'll see you all soon. Alrighty. Okay, sorry. Corinne, I'm sorry that this is how late this response is coming in, but I didn't see it before I left. Let's see. Let's see. Susan, great question. And you nailed it. Absolutely. Okay, so let's see here. So for not an ionic compound, ionic compound. For a compound to be an ionic compound, you need two things. You need a cation plus an anion. All right, for a or I shouldn't say an ionic compound. I should say an ionic bond. What makes up an ionic bond is a cation present with an anion. What makes a covalent bond a covalent so what makes a covalent bond is our electrons shared between two nuclei. All right? So there's only one way to have both. There's only one way to have both types of bonds. In the same compound. All right? And you need the cation, anion, or both to be a polyatomic ion. All right, that is the only way to have both a ionic bond and a covalent bond in the same molecule. And here's the reason why. Polyatomic ions all have covalent bonds. All right, every polyatomic ion has a covalent bond. So if you have a molecule like sodium carbonate, an ionic compound with a polyatomic ion, you have the ionic bond, which is the attraction between the negatively charged carbonate and the positively charged, sorry, that's a negative, positively charged sodium cations. All right, so this attraction is the ionic bond. But then you have the covalent bonds of electrons being shared between more than one nuclei inside the polyatomic ion. So that is the only way to have an ionic bond and covalent bond in the same molecule, is you need an ionic compound where either the cation, the anion, or both are polyatomic ions. If polyatomic ions are involved in your ionic compound, then you have covalent and ionic bonds both present. Did that help? Okay. Um, Number 3 in homework 5. I certainly can. let's see. Ah, yes, I can. Kate, great question. Okay, let's see. Okay, yeah, so let's see. So, Brianna, I'm looking up the number. Yeah. Totally. Totally. Kate V, you are welcome. Ah, yes. I would not mind at all. Let's see, chapter 5, 92, and 94. Oops. 92C and then 94C. Okay. Let's see. Alright, name the following binary molecule. Okay, cool. So we have to name and then also 94C. Okay, so first we've got P4O6, then we have H2SE. So actually I'm going to bump this down just a little bit. So both of these are covalent compounds, so it's just going to come down to their prefix names, and the prefix for 4 is tetra, and the prefix for 6 is hexa. So the first would be named tetraphosphorus. Hexoxide. And then the second, we'd have dihydrogen. And then because we only have one, we'd say mono. And now Se is selenium, so this would be monoselenide. I just wrote moselenide, hang on. Mono. Dihydrogen monoselenide would be the name of the second one. Okay, Susan. Let's see, we'll be able to see our past exams, quizzes, etc. Totally, okay. Totally. I need to look into the options right now. Right now in Canvas, you don't see the results for test security reasons. I need to look into the specific controls that they allow for instructors. That way I know just to see what all I can make available, how much can I make visible, how little. Because right now I just set it as default for just not to display results. Again, for exam security reasons, and so I need to look to see how much leeway Canvas allows. If it is like all or nothing, like you can see everything, you can see nothing, or if there's some middle ground. So I need to play around with the configurations. As of right now, the answer is no, but I will look into kind of what the parameters are, and I may be opening that up a little more in the future. Totally. Thank you for being patient and understanding. Of course. You are welcome, Kate. Oh, let's see. Lab 6, question 3. Oh, in the question section. Let's see, we have to determine here. Okay. So here, Carolyn, great question. So it says here, based on your limiting reagent, calculate the theoretical yield of silver in grams. And what you can do is, let's see, where's that part? So first thing you want to do is use data observations 5 and 6 to determine the excess reagent. All right, and the reason why this is important is the reagent not in excess is the limiting reagent. The reagent not in excess is limiting, and then step 3, use the initial mass of the limiting reagent to calculate the theoretical yield of silver chloride in grams. Does that Okay, kind of. Is there a specific formula that should be using for determining theory? Oh, okay. Carolyn, there's not so much a specific formula, but you take, so for example, It's just the process of. Well, here, let me write a chemical equation. All right. So to determine a theoretical yield, it's what we've been doing in class actually a lot between yesterday and today, right? It's taking an initial mass of a reactant, converting from grams of that reactant to moles of that reactant, then converting from moles of the reactant to moles of the product, and then the final step, going from moles of product to grams of product. And as always, you pull the molar ratios in from the balanced chemical equation, you calculate the molecular weights. So this is the calculation for awesome. Well done. Well stinking done. Let's see, homework 4. That's homework 5. Homework 4, number 15. Yeah. Of course. Anytime. Oh my gosh. You could hear him.
my gosh, that's awesome. Um, so I'm totally biased. But he kind of is.
Alrighty, well, I think it is time to put a wrap on this office hours. Thank you everyone for showing up, asking some great questions. Thank you everyone who is tuning in later. Hopefully you find it useful. And I will catch all of you tomorrow.